Good morning, students. Chapter 7, System of Particles and Rotational Motion. In last lecture, we have obtained one relation between linear velocity and angular velocity, scalar relation, and then vector relation. Now, in this lecture, we will see relation between linear acceleration and angular acceleration. Relation between linear acceleration and angular acceleration. Okay, yes, we will start from relation that we have obtained in last lecture. That is V is equal to omega cross R. You cannot write V is equal to R cross omega. Okay. Now we will differentiate this equation with respect to time. Differentiate this equation with respect to time t. Okay. Now see. Here, if you differentiate this equation with respect to time t, right hand side you have two quantities omega and r. Omega and r, they both depends on time. They both depends on time. So whenever you are given two terms in multiplication, and they depend on function on which you have to differentiate, then what is rule? Yes, there is one chain rule. There is one chain rule in differentiation, and that is if d upon dt of u is function of time, v is also function of time, and differentiation is with respect to time, then what is equation? D upon dt of uv is equal to u, first term as it is, dv upon dt, differentiation of second term, plus differentiation of first term, that is du upon dt, second term as it is. So yes, it is one chain rule that you have to remember. Clear about this? Yes, this rule you have to remember. D upon dt of uv is equal to u dv upon dt plus du upon dt v. First term as it is, differentiation of second, plus differentiation of first, second term as it is. Clear? Okay. Now, here we have to differentiate this equation with respect to time t. Then yes, it is dv upon dt is equal to two terms, omega cross r. Omega as it is, differentiation of second term, that is dr cross dt. Clear? Plus differentiation of first term, d omega upon dt cross r. Simple. Again, dv upon dt is equal to omega as it is, differentiation of second term, plus differentiation of first term, second term as it is. Now we know that differentiation of linear velocity with respect to time, it gives linear acceleration a is equal to omega cross dr upon dt, differentiation of position vector with respect to time, it gives linear velocity v. Okay, plus d omega upon dt, we know that differentiation of angular velocity with respect to time, it gives angular acceleration alpha. Here it is cross. Clear? So see, dv upon dt is a, omega as it is, dr upon dt is v, d omega upon dt alpha, and r as it is. Now see, a is equal to omega cross v plus alpha cross r, plus means this acceleration, this linear acceleration has two components. It has two components. First component is omega cross v and another component is alpha cross r. Clear? A linear acceleration has two components. Okay, first one is omega cross v and Second one is alpha cross r. Second one is alpha cross r. Clear up to this? Okay, linear acceleration has two components. This. Now we will draw one figure and we will find direction of omega cross v, direction of alpha cross r, and we will simplify this. Okay, but for that, first of all, we have to draw one figure. We have to draw one figure. See, figure. Here it is. Suppose it is axis of rotation. It is axis of rotation. One particle is performing circular motion on this circular path. It is its center. Let particle is here at point this. Its position vector is r. Its position vector is r. Let this particle is rotating in this direction. Let this particle is rotating in this direction. Okay, so as it is rotating in this direction, wrap fingers in this direction, thumb is in upward direction, means angular velocity is in upward direction. Or you can say angular velocity, and if axis of rotation is fixed, angular acceleration also is parallel to axis of rotation, and I will draw it like this. At this point also I can draw, okay, yes, here it is direction of omega and alpha. Clear? Yes, I can draw at each and every particle. Now as it is performing circular motion, it also has linear velocity, and that linear velocity, it is in direction of tangent. It is in direction of tangent. Clear about this? What is direction of omega? What is direction of v? Direction of alpha and direction of r. Clear about this? Again, we have to take one particle which is performing circular motion in this direction. Okay, in this direction, anti-clockwise direction. It is position vector. Yes. If you wrap fingers in this direction, thumb is in vertically upward direction, so it is direction of omega and alpha. Velocity, linear velocity at each and every point is in direction of tangent. Clear? Okay? Okay. Now what you have to do, see, from this figure, you have to find direction of omega cross p and alpha cross r. Omega cross p and alpha cross r. So yes, we will find. See, first, I am taking omega cross v component. Omega cross v component. Okay, chalo, omega cross v component. Now from figure you have to find its direction. From figure you have to find its direction. See, omega cross v. Here it is omega. See, here it is omega. So put your right hand in direction of omega. Wrap fingers in direction of v. Wrap fingers in direction of v. Thumb is in this direction, that is towards the center in radial direction. Towards the center or radial direction. Or if you do not want to use this right hand rule, then you can use right hand screw rule. Okay, omega it is in this direction, v is in this direction. You have to hold screw like this. You have to hold screw like this, and as it is omega cross v, you have to rotate screw in this direction. Okay, so if you rotate screw in this direction, the screw will advance towards center in radial direction. It will advance towards center in radial direction. Clear about this? Clear about this? Okay, so yes, you have two methods. Okay, first omega cross v, thumb it is in this direction, that is radial direction. So if omega cross v component K with the help of right hand screw rule, direction of omega cross v is in radial direction towards center. Therefore, it is called radial component. Therefore, it is called radial component of linear acceleration. Linear acceleration, and it is denoted by AR. It is denoted by AR. R means radial. Okay, so AR is equal to it is omega cross V. AR is equal to it is omega cross V. Okay, now if I want to find its magnitude, then AR is equal to it is omega V sine. What is angle between omega and V? What is angle between omega and V? See, if this object or particle is moving in this plane, then yes, omega is parallel to its axis of rotation, means in vertically upward direction like this. Yes or no? Why? This tangent, it is in plane of circle. It is in plane of circle. So if particle is here then, so yes, its velocity will be in this direction, while omega is in upward direction. So what is angle between them? Angle between them is 90. Angle between them is 90. Clear about this? Yes. We know that. Remember, the axis of rotation and plane of circle, it is normal. Axis of rotation and plane of circle is normal. This velocity is in plane of circle. Yes, this velocity is in plane of circle. That's why this omega and V, they are perpendicular to each other. So angle between them is 90. Sin 90, that is 1. So we can say it is omega V. Clear? Omega V. Okay. Now omega is equal to, we know one relation. We know one relation. That relation is V is equal to omega R. So omega is equal to it is V upon R. Omega is equal to it is V upon R. So if here I can write V upon R and here it is R, that is V square upon R. Clear? Here it is V square upon R. Or if you put here value, V is equal to omega R, then it is omega square R. Remember this result we have obtained in chapter number 4, uniform circular motion. Yes, it is nothing but radial acceleration. It is nothing but radial acceleration AR. It is nothing but radial acceleration AR. Clear about this? So yes, this omega cross V component, with the help of right hand screw rule, direction of omega cross V is in radial direction towards center. So it is called radial component of linear acceleration, denoted by AR is equal to omega cross V. Its magnitude AR is equal to only omega V or V square upon R or omega square R. Simple. Okay. Yes. Now, second component. Now, second component, that is alpha cross R. Alpha cross R component. Alpha cross R component. Okay. From this theory, from this first part, it is clear that radial acceleration, it is in radial direction. Yes or no? Yes. Alpha cross R component. Again, we have to see from figure. Alpha is in this direction. Yes or no? R in which direction? Yes, R it is in this direction. See. R is in this direction. See. Okay? So yes, first of all, you have to put hand in direction of alpha, that is in this direction. R, its arrow it is in this direction, so you have to have fingers towards R. So this thumb, it is in direction of V. This thumb is in direction of V, and V is in direction of tangent drawn at that point. Or with the help of screw, see, it is alpha and it is R. So if I put screw perpendicular to its plane like this, and if I rotate screw from alpha to R, okay, the screw will advance in this direction. That is in direction of V. Velocity is in direction of tangent. So simple. This alpha cross R component is in direction of tangent drawn at that point. So yes, you have to write the similar thing, that is with the help of right hand screw rule, direction of alpha cross R is in tangential direction at that point, and therefore it is called tangential component of linear acceleration. Therefore it is called tangential component. Therefore it is called tangential component of linear acceleration. Clear? It is called tangential component of linear acceleration, and it is denoted by AT. And this AT is equal to, it is alpha cross. Okay, its magnitude AT is equal to, it is alpha r sine. From figure it is clear, r is in plane of circle, while omega and alpha, they are perpendicular to it, so it is sine 90, and sine 90 is 1, so it is alpha r. So it is alpha r. So see, from this, what is conclusion? Yes, conclusion is, if one particle is performing rotational motion, okay, suppose particle is here, its linear acceleration has two components. First component is in this direction, that is AR, and second component, it is in this direction, that is A. Means linear acceleration has two components, and finally I can write this equation A as linear acceleration A is equal to AR plus A, and therefore its magnitude, how to write? A is equal to, it is under root AR square plus AT square, because AR is perpendicular to AT. They both are perpendicular to each other, so angle between them will become 90. So how to find the magnitude? A is equal to this under root AR square plus AT square, or I can say A is equal to under root AR means omega square V square, and AT means alpha square, and here it is simple. Okay, so yes, it is relation between linear acceleration and angular acceleration. Okay, yes, these two components you have to remember. If you have any doubt regarding this direction, okay, I will again explain this. See, it is direction of position vector. Linear velocity is in direction of tangent. As object is rotating in an anti-clockwise direction, wrap fingers in direction of anti-clockwise. Thumb indicates direction of omega. If axis of rotation is fixed, it is also direction of alpha. Now first component is omega cross V. So you have to put screw in a plane perpendicular to plane of omega and V. So plane of omega V, it is like this. So you have to put screw perpendicular to it. Okay, now rotate screw from omega to V, from first vector towards second vector. Then it will advance in this direction, that is radial direction, that's why it is called radial component. Similarly, for alpha cross R, alpha is in this direction, R in this direction, thumb is in direction of velocity. So yes, velocity is in direction of tangent, so this alpha cross R is in direction of tangent. So yes, that's why we have named radial acceleration and centripetal acceleration. Clear about this? Clear? Any doubt? Okay. Now, yes, here it is over. Now we have one special case, or we have one node. Okay, what is this node? See, if object is rotating with constant angular velocity. Now constant angular velocity means omega constant. Now omega constant means alpha is equal to 0, angular acceleration 0. Yes, it is simple. If omega, velocity is constant, means acceleration is 0. Yes, so alpha is equal to 0. And if alpha is equal to 0, then which component of linear acceleration will become 0? Yes, tangential component. AP is equal to 0. But AR is not 0. So in this case, what is linear acceleration? It is only AR. And it is omega v, or we can say v square upon r. So whenever, remember this note, okay, whenever object is rotating with constant angular velocity, its tangential acceleration is 0, it has only radial acceleration. And only radial acceleration means it performs uniform circular motion. It performs uniform circular motion. So yes, this note you have to remember. If object is rotating with constant angular velocity, omega constant, alpha 0, tangential component 0, but radial component is not 0. So A is equal to AR, means it has only radial acceleration. It is performing uniform circular motion. Clear about this? Okay, so yes, it is one important theory, which is relation between linear acceleration and angular acceleration. Yes, take care about these directions. Okay, try 1 or 2 times, you will get idea. Clear? So yes, it is one lengthy theory. So for today, this is it.